Hello, this is Group 18 and we are developing the portable unitary throwable target interceptor, also known as the P.U.T.I. Our group consists of 4 members: Alex Everson, me, Callum Fuller, Nathan Kimmel, and Jake Tattersall.
Hello everyone, and welcome to the demo video for Group 18. Our project is the portable unitary throwable target interceptor, also known as P.U.T.I. So we're going to start off with just a small general demonstration and explanation of how it works. So as you can see here, we've got our device with all of its internals exposed. So here we have the PCB, our Orin Nano, the radar modules, the motors, the laser, the camera, and the LCD. Alex is sitting there with the switch ready to turn it on. Currently it is off. And so what I'll be showing you real quick is just showing general functionality. So I have a green playground ball with me, which is one of our targets. And I will be showing you just how far it can move around, where it can actually see things, how well it tracks it. And then later on in the video, we'll go into the specifics. So for now, I will begin with the test. Before we begin, I will mention that the laser is a Class 3A laser. Generally, that means it is safe to be around without eye protection. However, all lasers are not safe when directly viewed by the eye. So I will be wearing these protective glasses. However, people like Alex who are behind it and out of range of it should not necessarily need these. So we will begin with the demo now. Thank you, Alex, for turning it on. Please turn it on one more time. There we go. That buzzer announces that it has been turned on. So, like I said, our target is this green playground ball. As you can hear by the buzzer, it's clearly been detected. Objects, like other green objects, aren't necessarily detected because our program uses some computer vision, not just some simple color detection or shape detection. This was detected because it was relatively ball-shaped, but as you saw, most of the time, other objects like that were not detected, and myself am not detected either, as well as nothing behind me, like this tree. But if we pick up the ball again, it's actively being detected, has a very wide range. This is much greater than the 120-degree field of vision. It goes 60 both ways, and detects it straight up above it and a little below the horizontal even. And when done, it resets to its starting position and turns off the laser and buzzer. That is the general functionality of our device.
Well, we have the humidity sensor here for our project. We have it implemented because we want to make sure that the temperature and the humidity for our radars and our camera isn't too high. Right now, the humidity sensor is reading at the temperature of our apartment and the humidity of the apartment, but when I blow into it, you'll see that the humidity increases as well as the temperature.
These are the microwave sensors used in our project. They are capable of determining the distance from the thrown object to themselves and are distanced away from each other at very precise measurements and angled different from each other to allow for X, Y, and Z coordinates to be triangulated using multilateralization.
This is our PCB. First we have the battery connector and the switch. These allow us to easily unpower the PCB and device, making sure the battery does not unnecessarily drain. Then we have the microcontroller, which is an ESP32. This is essentially the brain of the entire PCB and allows us to do computations and control the peripherals on the board. Then we have the I2C multiplexer. This allows us to communicate with multiple I2C devices through the same address. Since we're using 3 radars, this is necessary to be able to communicate with all 3 of them. Next we have the level shifter, which is used to convert 3.3 volts to 5 volts for the LCD. Then we have the buzzer. The buzzer is rated at 85 decibels at 10 centimeters away. Since we are using a magnetic buzzer rather than a piezo buzzer, we have a flyback diode. That means if there are any voltage spikes, it will not damage the transistor or the buzzer or any other components. Finally, since we have many external components, we need to have a lot of headers so they can be connected to the main board. First, we have the humidity sensor, which will be connected here. Then the 3 radars will be connected here. We then have the pan and tilt servos, which will be connected here. The 3.3 volt regulator is connected here. The 5.0 volt regulator is connected here. The 1.8 volt regulator is connected here. The LCD is connected here. And the laser is connected here. We also have a header to connect the UART from the main PCB and the microcontroller to the SBC here, and an additional header for UART to write code to the microcontroller. These are all of the regulators that we are using with the P.U.T.I. We have the 1.8 volt regulator, which is used to power the radars so they can gather data. The 3.3 volt regulator powers the humidity sensor. The buzzer allows the microwave sensors to boot and powers the microcontroller unit. We have the 5 volt regulator, which powers the pan and tilt servos, the laser, and the LCD. And then we have the 19 volt regulator, which is connected to the single board computer. Before we get into the tests we conducted to show the engineering specifications, I just wanted to quickly go over the remaining peripherals and explain them a little bit. So first we have the camera at the top of the picture here. This uses YOLO for the initial object detection to detect the green balls and is connected directly to the single board computer. Next we have the laser here in the middle of the screen. This is a 5 milliwatt laser, a class 3A laser as mentioned previously, and it is used as a visual cue to confirm that the ball or projectile was successfully attacked. Then we have the pan and tilt unit here, which is comprised of the 2 servos. These 2 servos will rotate to get the exact pan and tilt positions that we want, so the ball is always accurately and quickly detected. We also have the 3 radar modules, which Nathan briefly mentioned already. At the front, the humidity sensor is in the back corner, and then within the chassis, the PCB, batteries, and single board computer will be housed. With that, we can now move on to the testing of the engineering specifications. For the P.U.T.I, we have come up with a multitude of different engineering specifications. The 3 most important ones, and the ones we will be testing today, are the targeting response time, the range, and the target size. The targeting response time will be measured by using the large and the small ball in both stationary and moving states. Then we will use the stopwatch on the phone to measure how quickly the laser hits the ball. The range of the P.U.T.I should be able to detect objects from 1 feet to 5 feet or greater. We'll be testing this with, once again, the small and the large ball at distances of 1 foot all the way up to 7 feet to check for the target detection rate and the response time. The target size that the P.U.T.I should be able to detect and target should be greater than or equal to 6 inches in diameter. We will be using a smaller and a larger green playground ball, which Jake will get into next.
These are our 2 targets that we'll be showing off. This is our target showing the minimum size of approximately 6 inches. We chose these balls on purpose to show that generically the idea of a green playground ball could be seen by the camera, but even though there's different logos or different markings, they would still be identified as the same target. Our larger ball here is approximately 8.5 inches.
Small ball, stationary, trial 1. Stationary ball, small ball at 3 feet. Small ball, 5 feet, stationary trial.
This is small ball moving, 1 foot, trial 1. This is small ball, 3 feet, trial 2. This is small ball, 5 feet, trial 4.
We've already demonstrated that it can track the small 6-inch ball for about 5 feet. But now we just want to show that it can track the big ball to anywhere up to about 7 feet and more, but accuracy suffers.
Even though only a few of our tests were recorded, we conducted many more tests. We wanted to check that the ball was always detected for the smaller 6-inch and the larger 8.5-inch in both stationary and moving states, and check at all distances the target was detected. We found that in every single instance for the smaller and the larger at both states, the ball was always detected. There was only 2 instances where the target was not successfully hit by the laser, which was at 3 feet and 5 feet for the 8.5-inch ball when moving. This is quite an anomaly in the general schemes of things. Overall, you can see in every single test, the mean target time was less than 500 milliseconds, with the mean in the 6-inch ball when stationary being 0.358. The seconds when moving, it was 0.389 seconds. When the larger ball was stationary, the mean target time was 0.410 seconds, and when moving, it was 0.495 seconds. This means that we're able to successfully target the ball from all distances that we require and with a response time, target time of less than 500 milliseconds.